Section 16.7, Stokes' theorem. Only 2 sections to go, this one and 16.8. What's going on here? We want to construct essentially a 3D version of Green's theorem. I have a working green marker again. And in particular, we're going to care about the circulation curl version. Remember, we had 2 different versions of Green's theorem. Circulation curl is one of them here. So as a reminder, here's the statement of the circulation curl version of Green's theorem. And the idea is that the circulation of your vector field along the boundary of a region in the plane is equal to the double integral of this, what we called the k component of the curl here. So Green's theorem, let me just repeat that with a picture here. In the plane, okay, here is our region R. And the idea is that the boundary curve is C. The double integral, let me go in the other order first here. The integral along C of f dot dr, this is the circulation, is going to equal, by Green's theorem, the double integral of the, I'm just going to write k component of the curl of f here over R. Okay, so this is the circulation, this is the curl. That's why we say circulation curl version here. So the question about Stokes' theorem is, what happens if we go to 3 dimensions? What happens if our surface, instead of being in 2 dimensions here, what happens if our surface is, okay, I just drew here the top hemisphere, the upper hemisphere here, just the surface, not the filled-in hemisphere, just the surface here. And the idea is that, okay, right there is our boundary, and up here is our surface. Is there some kind of similar statement here that the integral along the boundary of the vector field is equal to something else? The answer is yes. That's going to be Stokes' theorem. We'll get there. Before we get there, we need to talk about curl. And so here is a definition of curl. We already talked about the k component of the curl. Remember that back here from our section on Green's theorem. We already talked about the k component of curl. Here is the actual definition of curl. The curl of a vector field f, m times I hat plus n times j hat plus p times k hat is curl of, sometimes we just write out literally curl of f, sometimes I'll write out this del cross f here. Del cross f is going to equal this expression here. So it might look complicated. It's, the partial derivative of the third component of f with respect to y minus the partial derivative of the second component of f with respect to z. All of that times I hat plus you can read out the rest of it for yourself. Now, this would be a lot to remember. It would be a lot to memorize if you had to memorize this from scratch. Fortunately, we have a shorthand way, a little way to compute it. And it comes from the idea of writing this as del cross f. Namely, if we think of del, the del operator as being a vector with 3 components, the partial derivative with respect to x, partial derivative with respect to y, and the partial derivative with respect to z, then this tells us exactly how to compute the curl. Because how do we do del cross f? We form a 3x3 determinant where the first entry here is I hat, j hat, k hat, just like whenever we do a cross product calculation. The third row here are the entries of f, m, n, and p, and then m, n, and p, just to remind you, those are all going to be functions of x, y, and z, probably. And then the second row here are partial derivatives. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And so if you then crunch out the cross product, like you know how to crunch out a cross product, you end up with, okay, the I hat terms will be this times this, but instead of doing partial derivative with respect to y times p, that just becomes partial p, partial y, minus the partial derivative with respect to z, sorry, partial derivative n with respect to z, plus, when we do the j hat terms, it ends up being the partial derivative with respect to z of m, partial z, minus the partial derivative with respect to x of p, and then plus partial derivative with respect to x of n minus the partial derivative of m with respect to y, all of this times k hat. So this is what we have here. And this is exactly what I wrote here. So how do you remember how to compute curl? This is how I do it. I'm not going to, I personally don't have all this memorized. I just set things up as this determinant to compute the curl of a vector valued function of a vector field, and this is how I do things. So as an example of this, let's calculate out the curl of this vector field right here. F is x squared minus z times I hat plus x e to the z j hat plus xy k hat. So the curl of f is going to equal I hat, j hat, k hat. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, and then x squared minus z, x e to the z, xy. Okay, what do we have here? We end up with I hat times the partial derivative with respect to y of xy, that's x, minus the partial derivative with respect to z of x e to the z, that's x e to the z. Okay, then for our j hat terms, it's going to be the partial derivative with respect to z of x squared minus z, that's minus 1, minus the partial derivative with respect to x of xy, that's y, plus k hat times the partial derivative with respect to x of x e to the z, that's e to the z, minus partial derivative with respect to y of this right here, that's 0. So in bracket notation, our curl here is x minus x e to the z, comma, negative y minus 1, e to the z. To wrap up this video, let me just point out one very important thing here. That curl of f is a vector quantity. It's another vector field. So we started off with a vector field up here. We obtained a second vector field down here. And I lied. I have one last thing and then we'll wrap up this video. I want to make sure that we realized here that when I called this the k component of the curl right here, partial n partial x minus partial m partial y here, I wasn't lying. That's exactly the k component of the curl right here. This exactly matches this. So this seems like a reasonable way to define curl.